So now we're going to take a look at the other broad category of polymers, which are synthetic polymers. And these, as we mentioned before, are not natural. So they're made in the laboratory, for example. They're not made by living things. So generally, we refer to synthetic polymers as plastics, which is just really a catch-all term for synthetic polymers. It's a wide category. The word plastics itself means literally molded, can be molded into different shapes. And one of the first plastics there was something called Bakelite, which you may have heard about before. But since then, there are all sorts of different plastics that have come about, and they have different properties that determine their uses. So really, if you think about where plastics come from, it all kind of comes from, if you trace the origins back to them, from petroleum. Different fractions when petroleum is fractionated can be used to create all these different types of plastics that we take for granted today. So we can classify our synthetic polymers in several different ways. The first is how the monomers are actually made up of. So we have what are known as linear, we have branched, and we also have cross-linked polymers. And we actually would see this as well in some of the natural polymers, like cellulose, for example, is linear. But you have other types of natural polymers um, like starches, for example, that do have branches in them, but we didn't really talk a whole lot about it then. But we will talk about it now. So this classification is based on the configurations of the monomer units that make up that polymer. So, for example, just as a block diagram um, of what a linear polymer would be. In a linear polymer, each strand or each component of it is just a long chain of bonded carbon atoms. Typically, carbon is the backbone for this. Again, we mentioned, last couple of weeks that carbon is really good at forming bonds to itself to make these really long chains. And it's essentially, as the name suggests, going to be in a line. Now, that linear arrangement doesn't necessarily mean a straight line. That it means consecutive carbon atoms that form the backbone one after another. That arrangement can maybe snake around itself. It doesn't have to be a straight line. It can zigzag. It can, form a circle, for example. It just needs to be a long chain of bonded carbon atoms. A branched polymer is one that has branches in it, as the name suggests. So branches that come off of the backbone. Okay, so you may have a long backbone, and periodically along that backbone, you have different branches associated with it. And then we have cross-linked polymers, where adjacent strands, adjacent meaning nearby, or adjacent backbones, if you will, are cross-linked, which just means chemically bonded via those cross-links. So whether it is a linear, a branched, or a cross-linked polymer, these will impart different characteristics to the polymers themselves. All right, so here we have an example, a depiction of the three types of categories so far. So we have these linear polymers. So again, if we were to highlight the chain here, it's in yellow, so it kind of snakes around, but it's a continuous chain. again, the backbone here is usually carbon atoms. And these linear chains can pack close together. And when these are heated, this leads to the melting of these of this type of polymer. So heating causes the softening or the melting as the strands separate from each other. If you take a look at the brand polymer here, so for example, if I have this here as my backbone in green, okay, you can see that I have a couple of branches that are in yellow that are kind of just coming off periodically from that main chain. So with the branch polymer, right, what this means then is because you have the branches that are present, these cannot pack as close to each other as in a linear arrangement. And because they're not smushed close together, that means it's less dense than the linear polymer. So these tend to be less hard and less brittle than a linear polymer. So these are easier to ignite. And these typically are going to be components of what are known as thermoplastics, which we'll talk about in the next section. Thermoplastics typically. Right, those are your branched polymers. The cross-linked polymers on the other side, we mentioned these are, you have a couple or several different strands. For example, this one here in green, this is one backbone. We have another one, another backbone over on this side. And these are connected to each other via these links. You can kind of consider them bridges that connect one strand or one backbone to the other one. And that's the cross link itself, right? So the yellow here is the cross link that connects one backbone to the other. So this then creates a three-dimensional mesh of that polymer strand, and it reduces the flexibility and it increases the strength or hardness and increases the melting point, right? So it's very strong. We have increased hardness as well because of the cross-linking, and it also increases the melting point of these compared to the branch or the linear polymer. And these are typically, your cross-link polymers are typically going to be, instead of thermoplastics, as with the branched, these are going to be thermosets. And we'll talk about that, what that is here in a second, as opposed to thermoplastics that we would see with the branched polymers. The other way that we can define our polymers is based on the type or the identity of the monomers or the building blocks involved. So we have two categories that can result from this. We have what are known as homopolymers versus a copolymer. So in a homopolymer, all the monomers are identical, right? So just as a simple example, if we identify our monomer here, let's say it's A. Well, if I have a bunch of A's linked together, right, that would be an example of a homopolymer and dot, dot, dot. All the examples we looked at previously were homopolymers. In a copolymer, the monomers are different. So you can have at least two different monomers linked together, maybe A and B. And then under this category, we can have what's known as alternate copolymerization. So for example, it goes A, B, A, B, A, B. So it alternates between one and the other. till you get to the end of the molecule. We can have random copolymerization. Okay, and that again, as the name suggests, it could be whatever. It could be A, B, 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 A, B, etc. So there really is no system in by which the monomers are linked to each other. So it's random, as the name suggests. And then we have block copolymerization, where the end of a chain of monomer 1 is attached to the end of a chain of monomer 2, etc. So for example, we can have a block of A's linked together, and then a block of B's linked together as well, and then that sort of repeats itself. So we have a block of A connected to a block of B, and so on. Right, so that's block copolymerization compared to random, and then we have alternate as well. We also have graft copolymerization. Oops, let's see here. A graft polymerization. This results in a polymer that is similar to a branched homopolymer, except that the backbone is monomer 1 and the randomly located branches are monomer 2. So for example, I can have an A all the way through, and then I have a branch coming off of this B's, for instance. Right, so that's a graft, because we're grafting B onto A. So the most commonly encountered of these families, the ones that you'll see most frequently, is the of copolymers is the terpolymer made up of 3 components. So 3 monomers, which is called the ABS copolymer, which stands for acrylonitrile butadiene styrene. So that's acrylonitrile. Butadiene and styrene. We'll take a look at these structures here in a second. But this 3 monomers are assembled in a copolymer that we'll see in a little bit. All right, so here we have the structures of the 3 monomers that we find in ABS. So we have acrylonitrile, which is this one here. We have butadiene, which is this, and then we have styrene, which is this one. Right, so all of these 3 linked together. You can see them sort of color-coded in our section here of that polymer. All 3 of them are linked to each other. And that ABS polymer itself has different properties compared to each of the individual monomers on their own. So the ABS is tough, hard, and heat resistant. But for example, the pure butadiene, so this, for example, is very rubbery. So kind of elastic on its own. Styrene, polystyrene, for example, has a smooth finish but is brittle. And acrylonitrile, the polyacrylonitrile, is durable, hard, and resistant to chemicals. So all 3 of these linked together now give us a polymer that has sort of a combination of those characteristics. We can vary the proportions of those 3 components, and you can tune the physical properties of the material such that this ABS is found in a whole host of different applications. You find them in things like waste pipes. You find them in plumbing fixtures. um, automotive trim components, medical devices, all sorts of applications depending on the percentage or the proportion of one component, one monomer versus the others. I'm just gonna say dot 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 here because there's a lot of applications for this. Okay, and just one last thing before we finish this section. A couple of the structures here are actually not correct. So I did try to change this here. This is from the GAN textbook. So butadiene actually has an H, it's in red over here, rather than a CH3. Okay, so cross that one out. That's not a CH3, that should be an H for butadiene. Acrylonitrile, this is just completely wrong. It's actually the C double bond C, and then on the bottom end here where the CH is, there should be a C connected to an N via a triple bond, right? So that's the correct structure for the acrylonitrile on its own. I just want to make sure that you have the correct structures when you're looking at these. It's not really ultra important, but in terms of having the correct structures and being chemically correct, you want to make sure that you have that. So just be aware of that when you look in your textbook. The structures on there are not entirely correct.